Hi everyone, in this video I will introduce my research about tackling safe and efficient multi-agent reinforcement learning via dynamic sharding. Background is multi-agent reinforcement learning has been increasingly used in safety-critical applications such as industry robots and autonomous driving cars. And existing multi-agent reinforcement learning methods cannot guarantee safety, especially during the learning process. However, learning with provable safety guarantee is necessary for many scenarios. Unsafe actions may cause serious damage. For example, autonomous driving car may collide with other cars or the pedestrians during training. So our goal is to design a safe and efficient multi-agent reinforcement learning framework. There are two challenge problems. The first is how to ensure safety, how to formulate the safety problem in learning and deployment process. And the second is how to design efficient algorithm to scale to multi-agent scenarios. We built our framework based on sharding. Let me explain. For traditional multi-agent reinforcement learning, the agents directly interact with the environment. But for sharding, it leverages the domain-specific knowledge to synthesize a shard in between the agents and the environment. And the shard will monitor the states and actions of the agents. If the agent generates unsafe action, the shard will correct it into safe action and also give a punishment to the agent. So the agent will learn to avoid that unsafe behavior in the future. And there is a dilemma in algorithm design that centralized method does not scalable to multi-agent scenarios, and fully decentralized algorithm causes conservative behavior because of lack of information. For example, centralized sharding synthesizes shard to monitor the whole state space. Fully decentralized sharding divides the state space into multiple parts and synthesize different shards to monitor each part. And for each shard, it only cares about the agents inside it, and it doesn't have information about agents in other shards. That's why it may has conservative behavior. For example, in this figure, if agent 1 want to move towards agent 2, and agent 2 want to move outside of shard 1, because shard 1 doesn't know whether there is an agent in shard 2 occupy this location, shard 1 will conservatively think agent 2 cannot successfully enter shard 2, so it will reject agent 1's action. So agent 1 will take an extra step to move to the desired position. And that's why fully decentralized sharding causes conservative behavior and lead to coordination overhead. To mitigate that, we propose dynamic sharding. Instead of divide the state space into different parts, we synthesize shards to monitor different agents, and we allow shards to merge with each other, and we allow a large shard to split into different parts. For instance, when agents gathering together, we allow the shards to merge into a large shard to mitigate the conservative behavior. And when agents move apart from each other, we allow the large shard to split into multiple shards to monitor agents concurrently so that it can improve efficiency. Here we prepare the demo video, and we can see when agents move together, the shards merge, and the position switch is really smooth and no conservative behavior. And when agents move apart, the shard will split into two shards and monitor agents at the same time. That's a basic idea of dynamic sharding. Now we talk about how to synthesize the shards. We propose a method called k-step look-ahead shard. First, we write safety specification in linear temporal logic. Basically, it's always no collision or other unsafe behavior. And we leverage the domain-specific knowledge to get the abstract of the agents and the environment and construct a two-player safety game. To win this game, at each time step, the state should satisfy the LTL safety specification, and we construct shard by solving this game. You can consider shard as a dictionary. When you input the state and action, it will output whether it's safe or not. And if it's not safe, the shard will output a safe action. And now we talk about the benefits of our shell synthesize method. The classic shell synthesize method is an offline algorithm. It do the computation before multi-agent reinforcement learning process, enumerates all possible states and actions that the agents may observe, and which takes a very long time. And for our shell synthesize method, we only look at the next case step, and after case steps, we recompute the shells, so it can highly decrease the computation complexity, and also because it's an online algorithm, it can capture unexpected environment changes. And this figure shows the word clock time for shell synthesize compared to this red line, which is classic method. Our method takes way less time. We also conducted experiments to test the performance of our algorithm compared to the benchmark in a grid world. Agents will learn to navigate in the grid world without collide with other objects or agents. And we measure the algorithm by the max reward, total step, and collision. From the result, we can see our algorithm has no collision, which means it ensures safety, and it has higher maximum reward, which shows its performance. And most importantly, our algorithm takes less steps to reach the goal than the fully decentralized sharding, which means it mitigates conservative behavior, and that proves that our dynamic sharding is effective. And finally, we acknowledge that this work was supported by CMU RISC program, Shenzhen AIRS, and CUHK Shenzhen. We are grateful to John and Rachel for organizing the RISC program, and I would like to thank Iwei and Professor Dolan for their insightful guidance. That's all about my presentation. Thanks for watching this video.